Don't forget to subscribe and ring that bell.
Hey there, what's going on? We are going to continue the 2018 AP Calculus AB exam. We are going to finish Section 2, Part A. We are going to do the second problem, free response question number 2. This is the last problem on this test that we are allowed to use a graphing calculator. Woohoo! And on the topic of graphing calculators, people always say, Visca, a wise and intelligent one, which calculator do you use? And my response is always the TI-84 Plus CE. Love the color edition. Comes in a whole slew of colors. Of course, my personal one is the all-time favorite, the all-popular, super sexy, boom, mint green. Yeah, ain't she pretty? Let's start free response question number 2. Number 2 says, a snail, one of the faster animals on the planet, is traveling along a straight path. The snail's velocity can be modeled by v of t, which is equal to 1.4 ln of 1 plus t squared inches per minute for a time between 0 and 15 minutes inclusive, right? A is asking us to find the acceleration of the snail at time 5. Okay, we should know, because this isn't our first rodeo, that there is position, there's velocity, and there's acceleration. We have velocity, we want acceleration. These are always one derivative away from each other, okay? So I need to take the derivative of velocity to get acceleration. So the derivative of velocity at 5 is equal to the acceleration of velocity at time 5. And what is that? Well, since this is the last problem that we get to use our calculator, I'm going to go ahead and use it right now. Here we go. I'm going to go to Math 8. I feel like I use, yeah, that's an error. I feel like I use the integration a lot in the calculator, but not the derivative function. So I'm going to take the derivative with respect to x of my velocity, 1.4 ln of 1 plus x squared, because we're not going to use t. This is the calculator. At what value of x? 5. And that's it, 0.538. This number will stay in 8 because the number after it is less than 5. So all I got to do right here is write 0.538. They don't ask for labels or anything. Goodness gracious, that's nice. B, what is the displacement of the snail over the interval from 0 to 15 minutes? Now, displacement talks about position, where it started and where it ended. It's really area under the curve, or if this is velocity, acceleration, and what was that, inches per minute? Yeah, we have inches per minute. So why don't I explain it this way? This is my inches per minute. This is my inches per minute squared, and there's position, okay, which is just inches, okay? They gave me velocity. Velocity was 1.4 ln of 1 plus t squared. Sorry, I'm writing sideways. There we go. I have velocity. I want position. Okay? If I were to go forward from position to velocity, that is derivative. But I have velocity, I'm going backward, which means I need to integrate. And oh, look, here are my bounds for my integral. So I'm going to integrate v of t dt, which is this thing right here, from 0 to 15. And that should give me the displacement of the snail. All right? So in my calculator, obviously in my calculator, I've got to put this in for my integral. But on my paper, if I write this, as long as you have your dummy variable, that still shows the people who are grading it how you're going to get your answer here afterward, okay? Because you're integrating velocity. So let's grab our calculators, and we're going to integrate math 9, get rid of this little arrow, as pretty as it is, and from 0 to 15, we're going to integrate 1.4 ln 1 plus x squared. We have 2 open parentheses, so we need 2 closed parentheses, dx. All right, now it's a snail. It's not going to go in 15 minutes 35 miles. If it does, I mean, let's use some common sense. You know, if you get a number that's astronomically large, you've made a mistake. But this is in inches, 76.043. So let me pop this out here for a reason. And the reason I wanted to pop this out here was this is absolutely fine. I can say 76.043. It doesn't ask me to label it, but I'm going to. Okay, I can have this in my paper, or I could have written it like this on the paper. Okay, either way, if you know what you're doing, I mean, you're doing this, and actually on a lot of answer keys you might see, especially from College Board, they would write the VT there, because you know that equation for VT is what you're integrating. All right. All right. C can be tricky if you just automatically start going in a different direction, but I guess that can be said of any problem. But let me explain here, because I think the way this is worded and what they give you is a little, can be easy to confuse. At what time t? Okay, so right off the bat, I'm trying to figure out a value for t. At what time t, between 0 and 15, is the snail's instantaneous velocity equal to its average velocity over the interval from 0 to 15. Now, here's the issue. When we think velocity, we think derivative, and derivative is slope. So when we think average slope, we want to take the between 2 points, 0 and 15. We think change in y over change in x or whatever. But remember, they give you velocity. Okay, it's 1.4 ln of 1 plus t squared. Okay, they give you this velocity. You have the equation that you need to find the average of. You need to find the average value of the given velocity in this case. You don't have position and you're trying to find velocity. You have velocity, and they want you to find the average velocity, which means the average value of the velocity. Anytime we're finding average value, we are integrating from 0 to 15, which are our bounds. Okay? V of t dt, and I'm multiplying by 1 over the difference of the bounds. Okay? That's the important thing to do, and that's just going to help us find t. We want to know what time, we're still trying to find this, that the velocity actually equals what the average value is. So I'm going to have to take velocity and set it equal to whatever I get here, because this is the average value. So what value of t that I put in right here would make this equal to the average value of the overall velocity from 0 to 15. Okay, so first, let's put this in the calculator, this average value integral in the calculator, and get a number. All right, on. And let's go alpha y equals enter. And I'm going to type it in just as I have it written. I mean, we'll put the 15 minus 0 there. Math 9. And so that integral is from 0 to 15 of my velocity, which is 1.4 ln of 1 plus x squared, so in parentheses, dx. Okay? This is the average value of my velocity from 0 to 15. And I hit enter, and I get something lovely like 5.0695. Let's use that. 5.0695. So I need to figure out, okay, what time that I could put in velocity that would make velocity equal to exactly 5.0, say, yep, 06. Let's just write that over. I lost that battle, kids. 695. Again, I have a calculator, so I'm going to put the equation into y1 and put this into y2 and see where they intersect. Okay. 2, 2, 2, 2, 2. Let's store that value, store that into v for velocity. All right, there we go. So let's graph these two things. So the first one is 1.4 ln. This is my velocity now, 1 plus x squared. And in here, I wonder if I just put the v, that's what's stored in v, so I got to type the whole thing out. And let's graph this. There's the blue one right there. That's velocity. And here is the v, perfect, barely above 5. So actually, I don't care about negatives on the x-axis because my time cannot be negative. Time goes from 0 to 15. My x-axis represents time. And I really don't care about negatives on the y as well, so let's just do that. Here we go. This line is velocity. This is my v of t. And this is my constant. This is my average value. So I want to figure out, okay, if this is, what was that? Oh, boo. This was at 5.0695 right here. What value of time makes these two equal? Down here. What value in t? I've got to use second trace, my intersect function. Let's get close to the intersection, hit enter 3 times. Bang, bang, bang. And it would give me this time right here, 6.031. So if you want, I mean, you can probably sketch the graph for yourselves if you want. But this happens at a time of 6.031, and that's in minutes. Wow, I don't know what happened there. There you go. That was, you know, it was a lot to do, but not really if you're not explaining it and just doing it. 2D. An ant arrives at the snail's starting position at t equals 12 minutes. Okay, we got another player in the game. And follows the snail's path. During the interval from 12 to 15 minutes, the ant travels in the same direction as the snail with a constant acceleration, this is nice to have, of 2 inches per minute per minute. So acceleration of the ant is 2, and that's inches per minute, or I can say per minute squared. All right, this is of the ant. Acceleration. The ant catches up to the snail at time 15. The ant's velocity at time 12 is b. All right, so this is something else for the ant. The velocity at time 12 is going to be some b value. And find the value of b. So that's what we got to get. All right, so we have a snail here. Let's just kind of summarize what we got here going. We got this snail, comes up like this, has his face, good for you, back down, good, has some antenna, look at us go. Doesn't look like a snail until I do this. Okay, the snail goes from time 0 to time 15, okay? The ant, which he has an ant, he has antenna too, bigger body. And then I think he's another bigger body part here. He goes 1, 2, 1, 2. So I'm just going to do that. I think, who knows if they got 6 legs. I don't know. I'm not a science guy. I'm just a math guy. The ant, okay, starts at time 12 and goes to time 15. That's what they tell us here. But they cover the same distance. They both travel the distance what was the distance? If I go to part B, okay, the total distance was this right here. So whatever the snail traveled in all 15 minutes, 76.043, the snail also covered, the ant also covered in the 3 minutes he went. That was 76.043 inches. Okay, so the snail takes all 15 minutes to travel that distance. The ant only takes 3 minutes. He starts at minute 12 of the snail's journey and goes 3 minutes to 15 and covers the same and catches. He catches a snail at that 15-minute mark. All right. So what we need to do, first of all, we need to get the equation for velocity for the ants. If I integrate acceleration, I get velocity. So I'm going to integrate 2 dt. That will give me velocity. If I integrate acceleration, this is acceleration here. Okay, that's 2t. There are no bounds right now. So it's plus c. That's going to equal my velocity. All right. Now, how do I get that c? The only other number that I have here, I pulled, okay, from 2b, the distance. That is position. Okay. If I integrate velocity, I can get position in regards to the ant with the bounds, my lower bound 12 and my upper bound 15. All right. So if I integrate velocity, that would now give me, you got to do that dt. This would give me position. Okay, and not only do I want to do that, to avoid getting another constant unknown when I integrate this to t plus c, I can do it from 12 to 15 because I know the total distance he covers in this time. Don't forget dt. That total distance he covers in the time should be 76.043. All right, so I can't just start using the calculator yet because I have this unknown. All right, so let's integrate what we have. Let's integrate what we have and get the position equation for the ant. All right, this will become t squared, this one when I integrate it, plus any constant when I integrate it, we'll just get the variable with it. So I get t squared plus ct, and I want that from 12 to 15. And whatever that is, it should end up equaling 76.043. Now I have one unknown. This one unknown c, once I solve that, I can put that right here into velocity to get my equation for velocity. And that's what I'm going to do. And then I can plug a 12 into velocity and score. I get the b value that I'm looking for. So let's continue with our work here. We're doing good. Thanks for hanging. All right, here we go. So first I put the upper bound in. It's 15 in for t squared plus c times 15. This is with the upper bound minus putting in the lower bound of 12. So I put the 12 in for t and square it plus c times 12. And that should equal my 76.043. All right, let's do some math. This is 225 if I square it, plus 15c. Okay, this is 144 plus 12c, but I got to distribute the minus sign. So I get minus 144 minus 12c should equal 76.043. All right. Let's combine like terms. 225 minus 144. Oh, you stinky poops. 25, that leaves me 24. It's 100. Is that 76? Huh? I feel like I'm off slightly. Oh, remember that? That was beautiful. So let's turn this on. Again, this is the last problem. We'll get to use the calculator. So we're going on this kind of complicated problem. And it would be a shame if you got this far and just made one mistake. 81, see 76. I went 5 in the wrong, 2, 3 in the wrong direction. That doesn't matter. This is why we use the calculator. 81. All right, so here we go. Those two combine to be 81. Okay, then I have 15c minus 12c. So we plus 3c. Still equals 76.043. All right, well, it's 2 steps. Let's subtract 81. Then I divide by 3. So my c is going to equal, ooh, fancy numbers, 76.043 minus 81, and then divide it by 3. 1.652 negative. Wow. We are still not done. This, I told you this was a complicated problem. That C value, negative 1.652, is the C value in velocity. So velocity equals 2t minus 1.652. They want this time to be 12, and they want to know what it equals. Okay? So V of 12 is 2 times 12 minus, oh goodness, 1.652. Oh, Lordy. 2 times 12. Oh, get rid of my pen. 2 times, get out of here, 12 minus 1.652. This 22.348. Wow. The velocity at 12 is 22.348. And its velocity, it's inches per minute. And that is the speed of the ant right at time 12. That was a lot. But you know what? The drawings made it better. These just made this pop right there. Okay? So, complicated, yes. Calculator, it's nice to have. We're done. I'll see you guys later.
Don't forget to subscribe and ring that bell.